SwayamPrabha. Digital India. Educated India.
Hello, welcome to this lecture on biomathematics. In today's lecture, we will start discussing a new section on Fourier series and Fourier transforms. What is this Fourier series and Fourier transform? I will explain this, and as we go ahead later, we will understand why we need to learn this. So, in today's lecture, the title is actually Fourier series. So, I will discuss something about Fourier series. So, first let us think about why we need Fourier series or Fourier transformation. So, to begin with, let us think about Fourier series. So, at the beginning of this lectures, we said that mathematics is like a language, and you want to describe everything that we see in nature with some equations. We can precisely write a few things with equations, some mathematical equations, so that we can describe things using equations. That is the idea of mathematics. That is what mathematics does. Like mathematics describes things in nature using equations. Now, we also said that many of the things that we see, we also already saw that many things that we see we can describe with some equations, like we use various functions. So, we said that we use some function to describe that something we see in nature. And we already discussed like straight line, square, like parabola, hyperbola, sin x, cos x, e power x, and various functions we discussed, and we saw that these functions can describe some of those things that we see. Now, let us think about something which is not that easily that can be described with any of those known functions. Let us say some complicated curve which is very difficult to describe with this. Then we said we can write it in as combination of few functions. So, then we can write something more complicated as a combination of x square, or whatever. A combination of few functions will give rise to some other function which is not that easy to describe by just there is no one particular function exists to describe a particular line or graph, but you can use a combination of functions. So, if by extending this idea, it is argued that any periodic function, let us say you have a periodic function that is a function that is repeating. We discussed some periodic functions like sine and cos, and we also said that why we need to learn about periodic functions. Let us say there is some periodic signals, like periodically varying things. It is argued that any periodic function f of x, so that is what is shown here, any periodic function f of x can be written as sums of sines and cosines. So, using sines and cosines, we can write a periodic function f of x. So, that is what we do in Fourier series. In Fourier series, what we do is that we take a periodic function, and that you rewrite in terms of sine and cos, something that we know. So, what kind of periodic functions we can think of? So, let us think of some functions like, so let us say you have something which is repeating like this. So, if you want, you can call it a square wave. So, this is something which is just keep repeating periodically, but we do not know how to write an equation for this. It is not easy to write an equation for this. But the claim is that this particular kind of thing that we might see in nature, or we might see somewhere something like this. Such things can be written as a function, and some combination of sine and cos. So some combination of sine and cos can be used to represent this kind of a periodic function. This is the claim. Can you think of some other periodic functions? So we can even think of many kinds of waves. So there is something called sawtooth wave, like which is so if you have a wave like this, this can be described also by some function f of x, which is a combination of sine and cos. So this is, we can call this sawtooth wave. It's like a sawtooth. Like if you want a little more dramatic, you can draw this in a particular way like this. So let's say this increases and decreases slowly. This is one way, or you can also draw like this, increases like this. Then, okay, to be more precise, it's like you can draw if you want like this. So let's say it increases like this, then suddenly decreases, then increases like this, suddenly decreases. So this looks like a saw, like tooth of a sawtooth, right? So this is, you can call, this is going to be sawtooth function or sawtooth wave. It's like a wave. So the claim is even this can be represented in terms of sine and cos, some combination of sine and cos. So anything that you can think of, like you can think of a little anything more complicated than even any other function you can think of, that can be represented by this combination of sine and cos. That is this claim. And so how do we represent, how do we write an f of x? What is this f of x? So it turns out that f of x can be written as, so something like, so now a combination of sine and cos. So let's say a1 cos k1x plus a2 cos k2x plus a3 cos k3x plus dot dot dot. Then you can say b1 sine k1x plus b2 sine k2x plus dot 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 plus some constant c. So this can be the most general combination of sine and cos you can think of. It is a very general combination of sine and cos that you can think of. So the claim is that if you take some value for a1 k1, a2 k2, a3 k3 and all that, and c a1 a2 a3 b1 b2 b3 c all that, if you take some particular values, the function can look like either like a square wave or a sawtooth wave, or any periodic function can be represented something like this. So that is the claim. So what is the, let me repeat it once more. So in general it is written something like this. Any function f of x can be written as a0 by 2, which is just a constant. This by 2 you can remove, you can call it like a0 if you wish, just the definition of a0 changes, plus sum over n is equal to 1 to infinity an cos nx plus sum over n is equal to 1 to infinity b1 sin nx. So this is the claim that any function f of x can be written as a combination of sine and cos. some combination of sine and cos. We don't know what is ANs, that means A1, A2, A3, A4, we don't know those coefficients. We don't know BNs, the coefficients of Bn. We don't know what A0 is. So, our aim is that if you find out A0, An and Bn, we can write this function. So, the idea is that if you can somehow know this A1s, Ans, A0, An and Bn, we can get this function. That is the claim. Okay. So, how do we get this function? How do we get this A0 and A1s and An? It turns out that the way to calculate this A0, An, Bn, etc. are somewhat similar to what we did in, there is some analogy related to regarding the vector. In the case of vectors, what we did, in the case of vectors, we wrote that A is A I plus B j plus C k. So, we wrote in the vectors that A is A I plus B j plus C k. So, we wrote any vector. Now, A, B, C are some coefficients. And how do we get this A and B, A, B and C? So, in this vector case, we can write little a is equal to A dot I. You know that A dot I is nothing but this dot I, that means A I plus B j plus C k whole thing dot I, and we know that I dot I is 1. So, this is A and I dot j is 0. So, we use the property that I dot I is 1, I dot j is 0. So, using this property I dot j is 0, I dot I is 1. Using this property, we can write A dot I is A. Similarly, we can write A dot j is B. Similarly, A dot k is C. So, you multiply this vector with this k, that is what you did, and then you get the coefficient. Now, let us think about in a similar fashion here. So, let us now write into a 2D vector here for simplicity. So, we wrote A as, let me write A as alpha I plus beta j, alpha I plus beta j, and we know that alpha is A dot I and beta is A dot j. So, similarly, we can write f of x as sum over n is equal to 1 to infinity a n cos n x plus sum over n is equal to 1 to infinity b n sin n x plus some constant c. Okay. So, in fact, actually, if you wish, like this c can be written as, here itself we can write this from 0 to infinity. So, it will be a 0 here, but it does not matter. Let me write like this. So, now analogous to this, the way of finding a n, it turns out is that a n is equal to f of x. We found a dot product with I, a dot I gave you alpha. Similarly, you multiply with cos and integrate. So, multiply with cos and integrate, you get a. Similarly, you multiply with sine and integrate, you get b. So, the way of finding a and b are like this. So, look at here. So, a n is actually, to be more precisely defined as 1 over pi minus pi to plus pi f of x cos n x dx. So, you can see that cos is the a n is the coefficient of cos. So, you multiply this like this and then you get this, and b n is this, a 0 is this. Why a 0 is this? Just here you put n equal to 0. In the a n, if you put n equal to 0, you essentially get the same thing. So, essentially this is nothing but this itself is written in a different way, but that is fine. So, this is a n and b n can be defined in this particular way. So, how do we get a n and b n in this particular way? It is very simple. You take this f of x, multiply with cos x and see what we get. So, let us do that. So, let us do this. Look at here. So, f of x is sum over n a n cos n x plus sum over n b n sin n x. So, this is 1 to infinity. We can write this as 0 to infinity if you like. Okay. Now, what do we get? Now, let us multiply with f of x cos n x and integrate. What if minus pi to plus pi? So, what do you get here is equal to sum over n a n cos n x, and you multiply with cos n x here, and you integrate. So, this is what you do. And so, what happens? What do you get? You have an integral of cos n, and so for a particular value of n, so you have to do this properly. Do this. Actually, you have to write this as a particular value of m if you like, because to just not to confuse. So, it turns out that we have to use this particular property, that sin m x sin n x integral. So, if you look at here, if you use the property, some properties of sin and cos that you have to remember is that integral sin m x sin n x is equal to pi into delta m n. What does this mean? This means is that if you take sine of some constant times x and sine of some other constant times x, if these constants are not equal, if m and n are not equal, this is 0. So, delta m n is called Kronecker delta. So, delta m n is 0 if m not equal to n, delta m n equal to 1 if m equal to n. So, if m and n are equal, you get 1. If m and n are not equal, you get 0. So, if you take f of x as sum over n a n cos n x plus b sum over n b n sin n x, then you multiply f of x with some cos some particular function m, let us say, let me multiply this cos m x and integrate. What do you get? Sum over n a n cos n x cos m x integral dx. So, this, so for various values of n, this will be 0 for all values of n except this particular when n equal to m. So, when n equal to m, this is 1. So, you will get a m. A m is equal to integral f of x cos mx. This is what you will get. Am is equal to integral m of x. You expand this, you expand this and use this particular property that cos of mx into cos of nx is equal to 0 if m is not equal to n and is equal to 1 when m equal to n. So, if you use that, you will get this. So, then you get what you have written here. You get that integral f of x cos mx is equal to am. Similarly, if you multiply with sine, so now let us look at sine. So, similarly, if you f of x is equal to sum over n a n cos mx plus sum over n b n sin nx, let us say that is n here, cos nx and sin nx. So, in the previous case, we had to just say one more thing, we used also this property. So, in the previous case where we had here, when you multiply with this cos, so sin and cos will be multiplied here, and it turns out that the sin cos product is, as you see in this slide here, it is sin mx cos nx integral is 0. So, we use two properties, that cos mx cos nx is delta mn and sin mx sin cos nx is 0. So, if we use this particular property, these two properties are like those two properties that we used, like I dot I is equal to 1 and I dot j is equal to 0. We use these two properties. So, this just like we used I dot I is equal to 1 and I dot j is equal to 0, we use this two property that cos m cos, when cos and cos are same, it is 1 if all of them are 1 or same, m and n are same, otherwise if sin and cos it is 0. So, such things are called orthogonal functions, but we would not go into the detail of this. But if you use this property and write it, essentially what you would get is this particular result, that a n is equal to this and b n is equal to this and a 0 is this. So, we might come, if it is needed, one can directly substitute, multiply this f of x with cos x and expand it and see and use this particular property, and then you will get this. Use this particular property and then you get this result. You can verify this result by substituting this f of x, this particular formula for f of x here, and use this particular properties. If you use these two properties, you will get two properties. First, you will have to use this property and this property, then this property and this property. So, these three properties we will have to use to get this results. So, do this yourself, substitute here, take this particular result, look at here, and if you take this particular result, substitute the right hand side of this instead of this f of x here and expand it and use the property, these three properties, and you will end up with, you will see that you indeed get a n and b n and a 0. Okay. So, what is now, how do we know, can we do an example? So, we have this results and can we do an example? Okay, so let us do an example of a Fourier series. So, what is the example of? Let us first take the simple example. This is the example of a sawtooth wave, something we discussed. So, how do we represent this sawtooth wave? Sawtooth wave is, as we said, is like this. So, we can represent the sawtooth wave something like this. So, if you take these two intervals, like you take in between this, let us call this minus pi and plus pi as the two particular points. So, between this minus pi and plus pi, our function goes like a line. So, this is f of x when between minus pi and plus pi. Then pi plus, suddenly it falls down again, it behaves like a, so it just starts from here. So, between these two intervals, interval of 2 pi, right, minus 3 pi is this. So, between minus 3 pi and pi, it is like a line. Again, between minus pi and pi, it is like a line. But this point and this point are same. So, this point and this point are same. So, whatever is here is whatever is same as here. So, the difference between these 2 points is like 2 pi. So, when f of x plus 2 pi, the function is the same as f of x. So, here it is f of x, which is a line, and here it is repeating. So, this can be mathematically represented in this particular way. It can be represented as f of x equal to x for when x is between minus pi and plus pi. When you go to x plus 2 pi, you get f of x itself. So, for all other values, if f of x for every other interval, it is f of x itself, just like this line itself for all x plus 2 pi's. So, it is x itself for x plus 2 pi. So, that is the sawtooth wave that we saw. Now, how do we write this in terms of sine and cos? So, we learned in the previous case that if you have this function a, b and c, a, b and a0 can be calculated in this particular way. So, what is a0? A0 is integral f of x dx. So, if you look at here, a0 is integral f of x dx. So, that is what is shown here. A0 is integral f of x dx minus pi to plus pi. Now, what was our f of x here? In our case, f of x was x in the between minus pi and plus pi, f of x was x. So, that is what we said in the previous, that is what we said here, that f of x is x between minus pi and plus pi. So, what do we need? So, look at here, a0 between minus pi and plus pi, that is a 1 over pi, this is the definition. A0 is integral f of x is x dx between minus pi and plus pi. Now, what is the times 1 over pi? Now, what is this integral x of x dx between minus pi and plus pi? So, you can do this, which is integral x dx is x square by 2 minus pi to plus pi. The whole thing divided by 1 over pi. So, this is 1 over pi. If you apply these limits, instead of x I have to put pi, so it is like pi square by 2 minus pi x equal to minus, at x when x is equal to minus pi, it is minus pi whole into minus pi, which is pi square by 2 itself. So, it is pi square by 2 minus pi square by 2, which is 0. So, it turns out that a0 is 0, that is what we get. We get a0 is 0. So, this is what I have written here. A0 is the one of the first Fourier coefficients, which is 1 over pi integral minus pi to plus pi x dx, and this turns out to be 0. Now, what is the next one, which is an? An is 1 over pi minus pi to plus pi x cos nx dx. This also turns out to be 0, but let us see why this is 0. how this function is 0. Let us have a look at it. So, what do we have? We have, what do we want to calculate? We want to calculate integral x cos n x dx minus pi to plus pi. Now, we were saying that any function, so now this can be written as, if you want, this integral can be written as minus pi to 0 x, sorry, this is cos and sorry, there is an error in this. So, what we should actually write is that a n we want to calculate is minus pi to plus pi x cos n x dx. So, this can be written as minus pi to 0 x cos n x dx plus 0 to pi x cos n x dx. So, it is like a sum. Now, but it just here this is the negative part and this is the positive part. What we want to do? We want to make it a division at 0 and this function above 0 this is pi, below 0 it is minus pi. So, this is 0. So, now let us take a particular point here x is, and let us compare this with a, so this is x and this is minus some particular value of x. So, let us say x is equal to 1 and x is equal to minus 1. So, now let us put here x is equal to 1 and x is equal to minus 1 in this equation. What do we get? If you put x is equal to 1 and x is equal to minus 1, what we get is that this term becomes 1 cos n x, which n is 1, sorry, n x is 1, right, and this becomes, sorry, this becomes minus 1. So, the negative part becomes minus 1 cos minus n. So, the negative part becomes minus 1 cos minus n plus this plus this is 1 cos n. So, you know, cos of minus n is cos n itself, because cos is always cos of negative, cos of minus, cos is a cos of minus is like a cos of minus n. So, this is basically, this whole thing is 0. So, each and every term, whatever x you put, the sum of this will become 0. So, for every x value of, so this you can call this as an asymmetric function. That means, for all this x cos x is equal to minus of x cos of minus x. So, if you put x as negative value, you get exactly the same opposite. This, so the sum of this is actually true 0. So, if you do this integral, since it is an, the function is asymmetric, that is x goes to minus x, there is a negative sign coming, you will see that you can show that x cos n x integral is actually 0. So, there is an asymmetry in this function. If you plot this, you will see that for every value of positive x, there is exactly the same value with a minus sign for the negative x. So, if you sum of this, you will get the sum as 0. So, you can see that if you can do this integral, you will see that this is indeed 0. You can try doing this integral by integration by parts. So, like let us try doing that quickly if you want. So, let us do this integral x cos n x dx. So, we can integrate this by minus pi to plus pi. You can write this as integral u dv. So, this is u and you can write this as dv. So, we saw that integral u dv can be written as uv minus pi to plus pi if you have, and write uv in the limits minus pi to plus pi minus integral v du in the from minus pi to plus pi. So, you can do this. So, if you apply this formula, so this you can do integrate by parts, this is called integrate by parts, integrating by parts. So, if you do this, our u is x and dv is cos nx dx. So, this is equal to uv in the limits. So, that is x, and integral of cos nx is sin nx by n in the limits minus pi to plus pi v du. V is again sin nx by n into du is 1. So, this is what it is. So, now if you apply this here, what do we get? So, you get, if you apply this limits here, you will see that you get the first one sin n pi is anyway 0. So, this term will go to 0 because if you substitute for x instead of pi and minus pi, you anyway get this term 0. Here also now you have just sin nx by nx integral you have to do. So, you know that minus pi to plus pi sin integral has to be 0 because a sine function is any periodic function like this will have area under the curve same on both sides. So, the sine of this is 0. So, you can see that this integral essentially will go, this will lead to 0, this will also lead to 0. So, both these terms this will give you 0, so the answer is 0. So, you can convince yourself by doing this that the answer is 0. So, a n is also 0. Now, what we have to calculate is b n. So, if you do this, it turns out that b n is not 0. So, let us quickly do this b n calculation. So, b n is again 1 over pi integral minus pi to plus pi x sin nx dx. So, again you can do this integrate by parts. You can take this as u and take this as dv, and integral u dv a to b is uv in the limits a to b minus integral a to b v du. This is the standard formula for doing such integrals which we already discussed. So, if you apply this formula and take x as u and sin x dx as dv, the answer is u into v, u is x. If dv is sin x dx, sin nx dx, v has to be minus cos nx by n, because the derivative of this is this. If you take the derivative of cos nx, you will get minus sin nx, and with the minus sign it will be plus sin nx, and by n times n. So, there is a by n has to be there, so that it cancels. So, this is v is minus cos nx by n. So, here let us write cos nx by n with a minus sign in the limit minus pi to plus pi minus integral minus pi to plus pi. V is again minus cos nx. So, this will become plus cos nx by n, and dx is 1. So, cos nx by n, this is cos nx by n, and this is du, and du is 1. So, we have this. Now, what is this? So, this is anyway, this integral of cos of anything from minus pi to plus pi has to be 0. So, typically this will become 0. So, now what you have is this particular term. You can do this term, actually if you want you can do this, you know the integral of cos nx will be sine, and sine in the limit sine n pi is anyway 0. So, this is, you can see that this is going to 0. So, this will go to 0. Now, what you have is this particular term, which is minus x cos nx in the limits. So, what you have is minus x cos nx in the limit minus pi to plus pi. So, what you, if your first limit, if you apply, it is minus. So, if you take this and the first limit is pi, that is substitute everywhere, instead of x you substitute pi. So, it is like minus pi cos n pi by n, cos n pi by n minus, you apply minus pi. So, when you apply minus x, x is minus pi, it will become plus. So, this is minus itself. So, this is again pi cos minus n pi divided by n. You know that cos minus n pi is same as cos n pi. So, this will become minus 2 by n cos n pi plus some term which will essentially become 0. So, if you do this carefully, essentially what you get is exactly what we wrote here. Look at here, what you get, if you look at this slide, what you will get is that b of bn is defined as in this particular way, and then what you get is minus 2 by n cos n pi plus this sin n pi is 0. So, this term is 0. So, what you essentially get is minus 2 by n cos n pi. Now, this from n from 1 onwards only. So, n starts from 1 because that is the definition of Bn, from n equal to 1 only. So, this can be written as minus 1 whole power n plus 1 by n, because you know we have, so what the claim is that minus 2 by n cos n pi is same as 2 times minus 1 whole power n plus 1 by n. So, let us check for n equal to 1 first. For n equal to 1, what do you get? Minus 2 by 1 into cos pi. What is cos pi? Cos pi is, cos 0 is 1, cos pi is minus 1. So, what do you get? Sorry, cos, so yeah, cos pi is minus 1. So, what do we get here? So, what you get is minus 2 into minus 1, you get 2. So, you get this as 2. Now, what do we get from this side? This side you get 2 into minus 1, and there is a whole by n here. Yeah. So, when n equal to 1, you get 2 into minus 1 whole power n plus 1, which is 1 plus 1, 2. So, minus 1 square divided by n is 1. So, you get 2 here also. So, you get both 2. Now, n equal to 2, here you get minus 2 by 2, which is minus 1, into cos 2 pi. Cos 2 pi is 1. So, this is you get minus 1. So, here what do you get? Here you get 2 by 2 into minus 1 whole power n plus 1, n is 2. So, this is 3. So, 2 by 2 is 1. So, this is you get minus 1. So, this and this are exactly the same. So, you can write minus 2 by n cos n pi as 2 into minus 1 whole power n plus 1 by n. So, this is a way of writing cos n pi. So, essentially what you get is that Bn, the only non-zero term is this. A0 is 0, An is 0, Bn is non-zero, which is this. So you substitute this back in the f of x and you get, we had already found that f of x can be written as sum over n an cos nx plus sum over n equal to 1 to infinity. So you can write the 0 to infinity if you want, Bn sin nx. We found that an was 0, so the only remaining term was Bn, and Bn was found as Bn was found as minus 1 whole power n plus 1 divided by n times 2, and there is sin nx. So this is our f of x. So f of x can be written as 2 into sum over sin nx minus 1 whole power n plus 1 by n. So this is an infinite series. There are like many terms, but the claim is that if you sum this series, you will get this. If you do this sum infinite times, you will get this sawtooth like pattern, which is like this. This is the claim. If you sum this, you will get this. This claim kind of looks non-trivial because sine typically does not look sharp like this. Sine more looks like a very smooth curve, and by summing such smooth curve infinite times, you get some such sawtooth like pattern. That is the claim. So now let us examine this. Let us plot this. So now let us take only the first term. So what is the first term? So the first term here is, so the first term in the sum, just take only one term. So the first term is 2 times n equal to 1. So minus 1 power n plus 1, n plus 1, n is 1, so n plus 1 is 2. So minus 1 power 2 is 1. So 1 by n is again 1. So this is 2 sin nx. So this is the first term. First term is 2 sin nx. So let us plot this. So if you plot this 2 sin nx, you will get something like this red curve. But the sawtooth pattern will look like this. Will look like this and then again fall down suddenly, then again this, again fall down, this. So this is the blue curve is our function, but just if you take the one term alone, just first term alone, what you get is this. So first term alone will not be able to represent this blue lines. Now let us take the second term. So what is the second term? Second term is n equal to 2. So n equal to 2, so second term. So look at here, second term. What is second term? 2 into minus 1 n is 2. So 2 plus 3 is 2 plus 1 is 3. So this is 3. So minus 1 power 3 is minus 1. So this is minus 1 by n is 2. So this is, so second term is n is equal to 2. So if you do n equal to 2, you get minus 1 by 2 into sin 2x. So this is, so the first one was just sin x, first one was 2 sin x, n is 1, so it's just 2 sin x. Second term was minus 2 and minus half go, so it's like minus sin 2x. So the second term was minus sin 2x. So you add the first term and the second term. So you add this term and this term. So what do you get? The first two terms. So the first two terms are So if you take the two terms, what you get? You get 2 sin x plus minus sin 2x minus 1 into sin 2x. So this is the first two terms. If you in the series, if you expand the first two terms, let's see what we get. If you plot this particular function, if you take this as your f of x, there is only two terms in the sum of series. What do we get? Let us plot this and see. We get this. Let's look at here. It's slightly becoming better. You get this. So this is better than the previous one, this. So this is surely becoming better. Two terms is becoming better than one term. Now what is the third term? So let's look at the third term. If you look at the third term, so third term means what? N equal to 3. So if you take n equal to 3 here, what you get? You get the third term is 2 into n is 3. So 3 plus 1 is 4. So this is 1 by 4. 2 into 1 by 4. Sin n is 3. So sin 3x. So this is 1/2 sin 3x. This is our third term. So now we add 3 terms. So now we add one more term to this. So let us make it 3 terms. So if you plot 3 terms, what is our f of x? 2 sin x minus sin 2x plus the third term was half sin 3x. So let's plot half. Let's add this. So if you add this 3 terms and plot this as f of x, what you get is this. Look at here, in this plot here you get this. So 3 terms is better than 2 terms, slightly better. Similarly, if you add one more term, you get 4 terms. So this is 4 terms is further better. 5 terms is much more better. So the more and more you add, it was very different. One term was very different, second term became better, third term became little more matching with the blue curve. If you add one more term in the series, it became further matching with the blue curve. If you add another term, it pretty much perfectly, not exactly like, but it is becoming much better. So if you by just taking 5 terms, it's pretty close to the blue curve. So now if you take infinite terms, it will be exactly this blue curve. So it will be exactly like this blue curve here and suddenly falling, again this blue curve, falling, suddenly blue curve. So you essentially by adding many sines, you can generate a sawtooth pattern. So let's look this as a movie. So look at this as a movie here. So one term after one term, if we plot this, it's like a movie. So let's play this. First term, second term, third, 3 terms, 4 terms, 5 terms. So let's play just one term alone, 2 terms, 3 terms, 4 terms, 5 terms. So if you add 5 terms, you are already getting somewhat good agreement with the blue curve. So what did we do now? We used sine alone and generated, and sum of sines in some particular fashion generated something like a sawtooth pattern. So we could generate a sawtooth pattern by sines alone. So this is the essential idea of this is the essential idea of Fourier series, that by summing sines and cosines, we could generate any function we want. So, we just discussed one example. In the next lecture, we will discuss a couple of other examples more, so that we will see how we can write down any kind of shape, periodic shape that we want using sines and cosines. Because if we can write any shape into equations, you can imagine that it can have various applications. Let us say you have some particular shape of a shape that you see in biology. If you can write this in terms of sines and cosine, it will surely going to be useful. So, in the coming classes, we will discuss a little more examples, a few more examples, and make these points more clear. So, this is all for today's lecture. Thank you.